Afternoon, all of you, and I welcome you on behalf of Department of Applied Sciences and Humanities of Parul University. As we all know that today we have gathered for a webinar on the topic Artificial Neural Network, which would be presented by Trupti P. Shah ma'am, Dr. Trupti P. Shah, and let me introduce her first of all. Trupti Madam is an Associate Professor from Department of Applied Mathematics, Faculty of Technology and Engineering from Maharaja Sayajirao University of Vadodara. She has a long experience of 24 years in which she has taught UG and PG level of students. Her research interest includes controllability of dynamical systems, medical diagnosis of diseases using soft computing tools like neural networks, support vector machines, and deep learning, and many more subjects. And we have also got the pleasure of being a student under her, and I welcome you, ma'am, on this day. And you can please begin with your presentation, ma'am. Thank you so much for accepting our invitation. Thank you.
Thank you. Thank you very much for your nice introduction. Good afternoon, one and all present here. I am here to discuss about artificial neural network. So let me first share the screen. Can you see the screen? My screen is visible.
Yes, ma'am.
Okay. So, to discuss about the artificial neural network, I have considered very basic topics. Okay, I don't want to discuss very detailed portion of this artificial neural network, but I have started with very basic topics. So, if you are familiar with artificial neural network, for those this would be repetition kind of thing, and I am apologize for the same. But if you are really beginner of, you don't know anything about the artificial neural network, I am sure you will get definitely be benefited by this lecture. Okay, so let me start. Before I start, I have some acknowledgements. I am highly influenced by the video lectures on deep learning by Professor Mitesh Kapra, Department of Computer Science and Engineering, IIT Madras. And in this presentation, I have borrowed the ideas from this presentation. Also, for the machine learning portion, I have borrowed the ideas which is from this particular URL. Okay, so first I acknowledge this two things first. Now, as we know, artificial neural network is an advanced form of machine learning technique, right? So the question arises, what is machine learning? Are you familiar with machine learning? Suppose to understand the concept of the machine learning, I will spend some time on this particular topic. Then only we will be able to see actual flavor of this artificial neural network, see how it works, right? And how it helps in machine learning. So, machine learning is a form of artificial intelligence that enables computers to learn from data. This data is highlighted over here, rather than through explicit programming. So, what it says, machine learning is a form of artificial intelligence. It enables computers to learn from the data. See, we have written many programs, right? But all those programs were traditional programming we have done. We are using any high-level language. We have written the program. We give input to the program, and our program computes the output, isn't it? It does the processing, and it gives us the output. So, in the traditional programming, what we do, We give input data and the program to the computer, and this computer system gives us the output, right? Whereas in machine learning, here I have mentioned that we don't have to we don't have to do any explicit programming. Okay, so in the machine learning, what we have to do, we have to give input data and the output data, input and output data to the computer, and computer will create a model. Okay, it will create a program, or we can say it will create a model using some algorithms. Okay, this is what the machine learning is. So this is the basic difference between the traditional programming and the machine learning. Now, this machine learning technique is most popular technique for predicting the future value or classifying information to help the people in making necessary decisions. So we all know that we are all mathematics people. Most of we are from the mathematics background, right? So we know the meaning of the predicting the future value and classifying the information. Predicting the future value. So we have constructed the regression models. So using this machine learning technique, we can construct regression models and we can classify the information which helps the people in making the decisions. We are familiar with the classification problems also. The classification means what? Classification predicts the category the data belongs to. Suppose you have, here are some of the examples I have written. Suppose in a hospital emergency room, the medical officer or the administrator wants to classify the high-risk patient and the low-risk patient, right? So this is a classification problem. Then spam detection. Spam detection, we know that our modern email system is, it has the ability to automatically detect the spam, right? That is the system analyzes all the incoming emails and mark them as spam or ham. Ham is a typical term for non-spam emails. So this is the classification, okay, from valid emails and the invalid emails, or you can say spam and ham. Then sentiment analysis, and so on. Suppose you want to bifurcate or classify from people from good mood and bad mood, right? So based on the certain characteristics, you can classify them having good mood and bad mood. So this is what sentiment analysis. Another example, as I said, I just want to make focus on this high-risk patient from low-risk patient. Suppose, as I said, an emergency room in a hospital observes. Suppose that emergency room of a hospital observes 10 features, or you can say 10 conditions of the patient's newly admitted patient, and based on these 10 conditions, that 10 conditions may be, one of the condition may be the blood pressure, age of the patient, then fever, cold, and so on. Okay, so these are the conditions. Suppose there are such 10 conditions. Based on these 10 conditions, a decision has to be taken whether the patient to be shifted in intensive care unit or not. As we know, only the high-risk patients should be shifted in the ICU, in intensive care unit. So this is the classification problem. It classifies or it discriminates high-risk patient from the low-risk patient. Now, suppose the hospital administration has documented this input-output of this emergency room. Means inputs are, suppose this, I mean, Suppose this hospital administration has documented all this information. Means the patients having the condition, and based on this condition, what the decision is taken by the medical officer, whether the high risk or low risk. Okay. Suppose thousands of such records are documented. So using this documented record, we can create an intelligent system, right? Our intelligent system will learn from this data. See, I hope you are with me. This system will learn what is the input, and I mean, see, this the documented data has which information? All the 10 inputs, and based on this 10 inputs, the decision taken by the medical officer, right? That is the output or the label, we can say. It may be high risk or low risk. So using this thousands of records, we can develop an intelligent system, and that intelligent system will be will use this data, thousands of records, means this data, and it will create a model, right? Using machine learning technique, we can create a model based on this data, and this model, once it is created, it will classify the patient from high risk to low risk with a very high degree of accuracy. Suppose this using this data, as I said, thousands of data, a model is created, a program is created. So when any new patient arrives in the same emergency room, and there is no medical officer, then the people over there, suppose some technical assistant over there, feeds the input in this system, then system will automatically give the response as whether the newly admitted patient is high risk or low risk. So this is how the classification problem works using the machine learning technique. Similarly, for the regression, as we are all familiar with the regression, regression predicts a numerical value based on previously observed data, right? Prediction of rain, suppose using temperature and other factors, determining market trends, prediction of road accidents due to careless driving, or suppose you have housing data, suppose you have data related to the housing information. Suppose that housing data contains the information about plot area, number of bedrooms, then age of the house, etc., right? And the price of the house. So using this data, a regression model can be developed, and this model is used to predict the price of the house when we give the necessary inputs, right? So we can say that the regression problems and the classification problems can be handled or can be solved very easily and very accurately using this machine learning technique. Okay, now so with the help of the machine learning, we can develop intelligent systems, as I said, that are capable of taking the decisions on an autonomous basis, right? On an autonomous basis. And as we see, data is the core backbone of machine learning algorithm. Machine learning is used in every domain, for example, in medicine, healthcare, manufacturing, banking, and several other industries. This machine learning combines the computer science, mathematics, and statistics. Okay, it combines these three branches. Statistics is essential for drawing information, or it is essential for drawing inferences from the data, right? Mathematics is useful for developing machine learning models, and finally, computer science is used for implementing the algorithms. However, simply building models is not enough. We have to tune this model. We have to optimize the model appropriately so that it provides the results with high accuracy. So optimization techniques are also useful, are also very essential in machine learning field. Okay. Now, these are some of the machine learning algorithms: artificial neural network, support vector machine, extreme learning machine, deep learning, decision tree learning, and many more. We will be discussing on artificial neural network. As I said, artificial neural network is an advanced form of machine learning technique, right? And the most fundamental unit of artificial neural network is called an artificial neuron. Now, the question is, why it is called a neuron? Where does the inspiration come from? So the inspiration comes from the biology, and more specifically from the brain. We know that our brain consists of network of more than 100 billion interconnected neurons, and which are capable of taking very huge or very complex decisions, right? So the question is, if we want the computer to do this, what to do? Okay. जैसे brain is taking very complex decisions in a fraction of time. So we want the computer to do this. Okay. So if we want to make the computer which mimic the functionality of the human brain, then what to do? Okay. So simply what we have to do, we need a model which is similar to the brain. Right? We need a model which is similar to the brain. Then only it will work like a brain, right? So before we discuss about the artificial neuron, let me see how our biological neuron works and how by taking the inspiration from this biological neuron, how the artificial neuron is designed. So this is the picture of this biological neurons. You can see that it has dendrites. So this portion is called the dendrites. This dendrites receives signals from other neurons. Okay, it gives input. It takes the signal. It receives the signal from other neurons, and this is the soma. It is a center part of this biological neuron. So at this place, this information is processed and it generates some output. And the output generated by this at this place is now transferred as an input to the other neuron through axon. So axon transmits the output of this neuron, right, students? So this is what we these are the so this particular biological neuron takes the inputs from dendrites. It processes the inputs over here and it generates some output, and this output is now going through this axon as an input to some other neuron. And this is the synapse. Synapse is the point of connection with other neuron, right? We know it is said that an average human brain has around 100 billion neurons. 100 billion neurons. Okay. So our sense organs, you can see that our sense organs interact with the outside world. Okay. They relay information to the neurons in the brain. Some of these neurons may fire in response to this information, and in turn they relay information to other neurons to which they are connected to. Now this other neurons may also fire, and the process continues, eventually in a response, right? Resulting in a response. So suppose we watch some comedy serial, and at that time our sense organ is eyes. Okay, our eyes gets information from the scene of this comedy serial. Okay, this information goes to the neurons in the brain, and then it produces some output, and this output in this case may be the laughter, right? For example. So this is how the biological neuron works. Okay, and you see that how our eyes, how quickly this process has been done. Okay, so machine learning algorithms are used to build the computers which mimic the functionality of the human brain. Okay, which mimics the functionality of the human brain. Now, using the inspiration from this biological neuron, McCulloch and Pitts has proposed a highly simplified computational model of artificial neuron. This is artificial neuron. You can see that it receives the inputs, right, like dendrites. It does some processing over here, and then it gives the result, gives some response as an output, right? So it is similar to the biological neuron. So here the McCulloch, he was a neuroscientist, and Pitts was a logician. They proposed this model in 1943. Here, this inputs, you can see that inputs are binary. These inputs are only from 0 and 1. This particular neuron is divided into two parts. The first part aggregates, this G aggregates the information, and it simply does the addition of this information, right? This inputs. So G is a very simple function. It does the summation of these inputs. The other part, the second part, F, decides what is the aggregation, and based on that, it will decide whether to fire or not. Okay, it takes the decision whether to fire or not. Firing means if a neuron fires, it means the output is 1, and otherwise output is 0. So you can see that Y is some function of Gx. It is equal to 1 if here I have written this mathematical form of this rule. So if this Gx is greater than or equal to theta, some theta is a threshold parameter. Okay, it is some threshold value, and Gx is less than theta, the output Y is 0. Okay, this is how this McCulloch Pitts neuron works. Okay, now let us see the implementation of some Boolean functions using McCulloch Pitts neuron. Now, the question is why we are interested in implementing the Boolean functions, right? That is what the question is, why we consider the Boolean functions. So we know that in real life also, we take lots of decisions based on the Boolean inputs. Suppose we take a simple, I want to take a very simple decision to go for movie or not. Okay, my decision is based on, maybe based on the inputs like is actor Akshay Is genre thriller? Is director Nasiruddin? Okay. So you can say that these inputs are binary. This may have an answer as a yes or no. Is actor Akshay? Yes or no. Is genre thriller? Yes or no. Is director Nasiruddin? Yes or no. So these inputs are binary, right, student? And so on. Okay, this decision for going for movie or not is based on these inputs, and we see that based on these inputs, either I may go for a movie or may not go for the movie. So again, the output is also Boolean. Okay, so in real life, we take many decisions based on the Boolean inputs. And another thing is, these Boolean functions are very simple functions to understand the concept. So we use the Boolean functions to understand this particular concepts. Okay. Now, this is, you see the first figure. This is a very simplified representation of the McCulloch Pitts neuron. It takes 3 Boolean inputs. It has a certain threshold. If the sum of these inputs is greater than this threshold, then the neuron fires. That is what the rule is, right? The rule is, if sum of these inputs is greater than or equal to some threshold, then only the output is 1. So likewise, so using this model, suppose I want to implement, I'm trying to learn this AND function. So will you tell me what should be the value of threshold? I have already mentioned over here, but we know that this AND function, we know the truth table of the AND function for 3 variables. See, there are 3 inputs now. So how many possible data points would be there? How many possible data points would be there? It would be 2 raised to 3, right? 2 raised to 3, that is 8. And we know that this AND function fires if all the inputs are on, or if all the inputs are 1. Okay, then only the output is 1. Otherwise, output is 0. So what should be the value of theta in that case? Theta must be 3. Right? Theta must be 3. Similarly, for the OR function. For the OR function, what should be the theta? Theta is 1, because we know the truth table for OR function also. Okay, if any of the input is 1, output is 1. Okay, so this is how we compute the threshold. Okay, and so here in MP model, learning the MP neuron is nothing but obtaining or finding the value of this theta, right? Finding the value of this theta. I hope you are with me. Now the question is, can any Boolean function be represented using this MP neuron? Okay, any kind of any function can be implemented using the MP neuron. That is the question. But before we answer this question, we see the geometric interpretation of the MP model. So geometric interpretation of the MP model, to give the geometric interpretation, I have taken the only this very basic example or function with 2 inputs only. Okay, with 2 inputs. So what should be the decision function over here? X1, if x1 plus x2 is greater than or equal to 1, then only the neuron will fire. Otherwise, the neuron will not fire. So here, threshold parameter is 1. So if you ignore this greater than part, and if you consider only the equal part, then you will have x1 plus x2 equal to 1. Right? X1 plus x2 equal to 1. So this x1 plus x2 equal to 1 is an equation of straight line, and that equation, that line is this, right? This is the line equation of this x1 plus x2 equal to 1 line. Now, what we see here, we see that all the points, this is OR function, right? All the points for which output is 1, they are lie on or above or on the positive side of this line. You can see that for 0, 1, output is 1. So that point is on the line. For 1, 0, output is 1. So it is also on this line. And for 1, 1, output is 1. So all the points for which output is 1 are either on the line or on the positive side of the line. And for the point, this point is 0, 0. See, for two Boolean variables, only 4 data points are possible, right? These 4 data points are 0, 0, 1, 0, 0, 1, and 1, 1. For 0, 0, output is 0. So that point lies on other side of the line. So what we see here, this MP model, MP neuron splits the input points into 2 halves. Okay, it classifies these 2 types of inputs. Inputs producing the output 1 on one side, and inputs producing output 0 on other side. So this is the AND function. Similar example here, AND function. We know that for the AND function, the threshold is 2, and so the equation is x1 plus x2 is greater than or equal to 2. Again, if we ignore the greater than and consider only the equal, then my equation of the line would be x1 plus x2 is equal to 2. This is the line. You can see that only 0.11 lies on this line, and only for this point output is 1, and for other 3 points output is 0. So they lie on the other side of the line, right? Other side of the line. So it classifies this simple McCulloch Pitts model, gives us the decision boundary, right? This is the decision boundary. It is a straight line for 2 dimension. It is a straight line. But what if we have more than 2 points? Suppose we have 3 points, x1, x2, and x3. We have 3 inputs, and we are implementing the OR function only. For 3 inputs, the equation, instead of the straight line, our decision boundary would be the plane. It would be a plane, right? The equation of the plane is x1 plus x2 plus x3 is equal to 1, right? You can see that for the OR function, only the point 0, 0, 0 has a value output as 0. So that particular point lies on other side of this plane, whereas all the 7 points, other 7 points lie on other side of the plane, right? So it classifies 2 types of patterns, you can say. So a single McCulloch Pitts model neuron can be used to represent Boolean functions which are linearly separable, okay? Which are linearly separable. Now the question is, see, so far we have considered only the Boolean inputs, but what about the non-Boolean or real inputs? Do we always deal with the Boolean inputs? No. We don't always, our inputs will not be the Boolean, right? Now suppose we consider the example where you are the oil mining company and you are trying to decide whether you should mine or drill at a particular station in the ocean or not. Okay, are you with me? Suppose you are a oil mining company and you want to decide whether you should mine or drill at a particular point or at a particular station in the ocean or not. So this could depend on various factors like what is the pressure of the ocean surface at that point, what is the salinity of the water at that point, what is the marine aquatic life at that point, and so on. We see that these inputs, right? These factors are not Boolean. These are all real numbers. Pressure would be a real number. Salinity would be a real number. Density is a real number. So this is also very valid decision problem. Companies would be interested in doing this. So in such cases, inputs are going to be real, right? So we can see that here in this example, inputs are real, but output would be what? Either to drill at that place or not. So output is yes or no, to drill or not to drill. Okay, so it is a Boolean, right? We know that MP model cannot solve such type of problem, right? So this is the limitation of the MP model. It doesn't take any real input. Okay. Now another limitation is in the MP model, how we computed the threshold. We did some manual computation, right? And we computed the value of threshold. But this is not going to work in a larger problems where you have many more dimensions and inputs are no longer to Boolean. Okay, so this is another limitation. McCulloch Pitts model threshold, we hand coded the threshold value, no? So it is not possible for the larger problem, right? It is not possible. Suppose you have thousands of input, then how will you hand code the value of the threshold? So this is the limitation. So we need a way of learning this threshold, isn't it? We need a way of learning this threshold. We should have some algorithm which computes the value of this threshold, right? Another problem with the McCulloch Pitts model is all the inputs have equal importance. So the question is, are all the inputs equal always? What if we want to assign more weight or more importance to some inputs? Suppose in the movie example, suppose I want to give more importance to the my input is director Nashiruddin. Okay, I don't mind whoever is the actor and whether the genre is thriller or not. I don't want to. It is not that much important for me. Suppose. So in that case, I should give the import. I have to give some importance to my input. So in McCulloch Pitts model, it is not possible, right? All that in that model, we cannot give the weights or attach weights to the inputs. And the fourth problem is, what about the functions which are not linearly separable? As I have mentioned, it represents only the McCulloch Pitts model represents only the Boolean functions which are linearly separable. So what if the functions are not linearly separable? So these are some of the questions. So to answer these questions, we see here, we fix some of the problems using this Perceptron model. Okay, So this is what the perceptron model looks like. This is the perceptron model. It is, you can say, it is a generalized form of the MP neuron. It is generalized. What is the difference? What is the difference you see here? The weights are attached to this inputs. Okay, and also we have the mechanism of learning these weights. We have the mechanism of learning these weights. Okay, also the inputs in the perceptron model are no longer to the Boolean value. They can be real. Okay, so in the perceptron, these inputs can be real. Each input has attached some weights, and these weights, we have the mechanism of learning these weights. Okay, here you can see that the summation is the weighted sum, right? So summation of Wixi, if the summation of this quantity is greater than or equal to theta, the output is 1. And if it is less than theta, output is 0. So it is similar to this our McCulloch Pitts model. So this particular model, firstly proposed by Frank Rosenblatt, an American psychologist, in 1958. Then Minsky and Peppert has carefully refined or modified and analyzed this model in 1969, and the model which is given by this Minsky and Peppert is now referred to as the perceptron model. So this is the model which is given by this Minsky and Peppert, right? So it is very similar to this McCulloch Pitts model. We can see it again divides the inputs in two halves. The input for all the inputs whose output is 1 lie on the one side. Inputs whose output is 0 lie on the other side of the line or plane or whatever it is, right? So now these equations of the perceptron model can be slightly rewrite. We can rewrite this equation in this way. I take theta in this side, right? Now instead of taking this threshold as a separate quantity, I take one of my input. I take one of my input is always 1, and the weight of this input is minus theta. Okay, you can see in the next figure. I take one more input. I say it is always 1, and weight attached to this input is minus theta. Sorry. So this particular model, so this theta minus theta is now attached over here, so we don't have to write it separately in this form. So this is a more accepted convention of writing the perceptron. Okay, y equal to 1. If okay, one figure is not y equal to 1. If this summation is greater than or equal to 0, and it is 0 if this quantity is less than 0. I'm missing one equation over here, right? So here x0 is 1 and w0 is minus theta. So this is the perceptron model. And as we see from the equation, as I said, it is clear that even a perceptron also separates the input space into two halves. All the inputs which produce 1 lie on one side, and all inputs which produce 0 lie on the other side. In other words, a single perceptron can only be used to implement linearly separable functions, right? And the weights can be learned and the inputs can be real valued. Okay, we have the mechanism for learning these weights. Let us see one example of the perceptron. Here I implement the OR function. We know that for 0, 0, output is 0. This is the truth table. And from the equation of the perceptron, 0 means this weighted sum is less than 0. Output is 1. It means this weighted sum should be greater than or equal to 0, right? Here also output is 1. So this weighted sum should be greater than or equal to 0. Okay. Now if you plug in this x1 and x2 in the first equation, so put the first pattern x1 equal to 0, x2 equal to 0 in this particular inequality. Okay, in this inequality, first inequality. So what we have, w0 plus w1 into 0 plus w2 into 0 is less than 0. So what does it imply? w0 is less than 0. Similarly, you put 1 and 0 in the second inequality. Okay, x1 as 1 and x2 as 0 in this second inequality. So this second inequality produces w2 greater than w minus w0. Similarly, from the third pattern, I'm sorry, if you plug in this value, you will arrive at this inequality. W1 is greater than minus W0. And for 1, 1, you will get W1 plus W2 is greater than minus W0. Now we are in search of the value of W0, W1 and W2, which satisfies all the four inequalities. So I take one of, there are several solutions, okay? There are various possible solutions available. But one of the solution is, suppose I choose W0 equal to minus 1. W1 equal to 1.1 and W2 equal to 1.1. Okay, so W0 equal to minus 1, it satisfies the first inequality. Yes, minus 1 is less than 0. It satisfies. Now W2 is greater than minus W0. W2 is what? 1.1. 1.1 is greater than minus into minus, so minus plus. So 1.1 is greater than 1. W1 is also 1.1. So 1.1 is greater than 1. And addition of these two, W1 and W2, is again greater than minus W0, right? It is greater than 1. So we can see that this set of values of weight satisfies all the four inequalities, right? So using this, and there are many such possible solutions. So using this three values, when I put these three values in the equation, I will have minus 1 plus 1.1 x1 plus 1.1 x2 equal to 0. I will get the equation of the line, and this line is, suppose, this line. Okay, you can see that I got the equation of the line. Using these values of W0, W1 and W2. And here we see that these 3 points for which the output is 1 they lie on the line or above the line, and the point 0, 0 whose output is 0, which lies on the other side of the line, right? So we can see that it is similar to the McCulloch Pitts model, but here we have the algorithm which learns this value. Okay, that algorithm computes the value of W0, W1 and W2. Here the computation is very simple, so we have hand-coded the computation. But for the larger problem, we have the mechanism for computing these values. So I hope you are following. So this is the equation of the, so see, what you have to see, using these values of W0, W and W2, W1 and W2, you have built a model, right? And this model will now predict, suppose any unseen pattern has arrived, then this model will find out whether it will lie on this side of the plane or it will lie on the other side of the plane. Okay. Okay. So for using the data here, this is a Boolean case. So we have only 4 inputs. So using this model, we have using this input-output data, we have constructed the model, and this model is now capable of predicting the unseen data which arrives to the system. Okay, it will correctly classify that whether that point produces the output as 1 or 0. Okay, it will correctly classify the any unseen data. Okay. Now let us see what is errors and error surfaces. This is now let us fix W0 equal or minus W0 equal to 1, and let us try the different values of W1 and W2. Suppose I take W1 equal to -1 and W2 equal to -1. Okay. So see, W0 is -1, W1 is -1, and W2 is also -1. So it will give me the equation of this line. I hope you here I am pointing. So this is the line. This is the line. Okay. The equation of line is given by this equation. So this is not this line is not a perfect line. It doesn't classify the points in doesn't classify the point correctly, right? So how many errors we have made in this particular decision line? So 0, 0 point should be on the other side of the line. Other 3 points are on the correct side of the line, right? So I made one error. 0, 0 is wrongly classified. Okay, it lies on the positive side of the line. So it is wrongly classified. So when I choose W1 equal to -1 and W2 equal to -1, I commit one error. Now suppose I choose W1 equal to 1.5 and W2 equal to 0. Then then I will have this line, this horizontal, this vertical line, right? ये जो vertical line है, this is the equation of the equation of the line is -1 plus 1.5 x1 plus 0 into x2 is equal to 0. So if I construct this line, we can see that these 2 points are correctly classified, 1, 0 and 1, 1. But this 0, 1 is wrongly classified. 0, 0 is also fine, but 0, 1 is wrongly classified. This point should be on the positive side of this line. So I committed one error. If I take a W1 equal to 0.45, I'm sorry, and W2 equal to 0.45, then then this is the equation of the line, right? So when I construct this line, how many errors I have made? 0, 0 is correct, but these 3 points should be on the positive side of this line. So I made 3 errors over here, right? Now, so we are interested in those values of W0, W1 and W2 for which the error is 0. Error is 0. So let us plot the error surface. So this is what the error means, right? Okay. Now, when you plot these errors, you will arrive at the for different values of W0, W1 and W2, you will come across the errors. So when you plot these errors, then you will get such type of error surface. See, for case of this analysis, we keep W0 as -1 fixed. Only I am changing W1 and W2. W0 is fixed and it is -1 I have taken. And for different values of W1 and W2, the error has computed and these errors are plotted. So it will give me this error surfaces, right? Error surface. You can see that at this point, the lowest error is at the place in the graph where this is dark blue color surface has very less error, right? So we are interested in the algorithm which finds the value of W1, W2 and W0, which minimizes this error. In other words, we want the perceptron to find the equation of the separating plane. So this is the perceptron learning algorithm. See, we have very principal approach of learning this weight. Okay, mathematically you can. Here I just demonstrate the algorithm, but mathematically we can visualize it. How this particular algorithm converge, right? So see, we have certain positive inputs and certain negative inputs. Positive input means output is 1. Negative inputs means output is 0. Now what we do here, we randomly initialize. See, we don't have any knowledge of weight, right? We don't have any knowledge of weight. So I initialize W, this vector W randomly. So when we do initialize it randomly, of course we will make some errors, right? So suppose I write this loop. Now I pick some random point X from P union N. Okay, I take any X input pattern from this union. Now suppose X belongs to P and this summation is less than 0. So then this is the case of error. See, when X belongs to P means the X is a point whose output is 1. So in that case, this weighted sum must be greater than or equal to 0. But due to the choice of this W, this weighted sum is less than 0. So error has occurred, right? So if X belongs to P and this sum is less than 0, then W equal to W plus X. Okay, it is very simple algorithm. And if X belongs to N, means this is the point for which the output is 0. For the 0 output, this weighted sum must be less than 0. But here it is greater than or equal to 0. So in this case, you have to simply subtract the X vector from W. And you have to repeat this process until the convergence. What do you mean by the convergence of the algorithm? And it is not making any more errors, okay, in the training data. So when you see that there is no error in the training for the training data, then you say that your algorithm has converged, right? Now the question is, who gives us the guarantee about the convergence of this algorithm? So to help to take this decision, we have the Perceptron convergence theorem. The Perceptron convergence theorem says that if the patterns are linearly separable, then this perceptron learning algorithm will converge in finite steps. Okay, it will converge in finite steps. So this is the guarantee given by the perceptron convergence algorithm. So algorithm which we have seen will converge in finite number of steps if these patterns are linearly separable. I hope you are with me. So we could answer almost all the problems. Only the last problem, what about the functions which are not linearly separable? You know, that is not answered using a single perceptron. See, up to this point, we have considered only the single perceptron. So using the single perceptron, we cannot classify the patterns which are we cannot classify the patterns which are not linearly separable. So the question is what to do, how to handle this situation. I skipped this line because we are not having sufficient time. This is the XOR problem. Here you can see that for the XOR, it is it is not a linearly separable Boolean function. For 0, 1 and 1, 0, we know that output is 1 and for 1 1 and 0 0 output is 0, you cannot separate. देखो यहाँ पे मैं कोई भी लाइन ऐसा नहीं बना सकती कि ये दोनों पैटर्न सेपरेट हो जाए, right? So it is not linearly separable. It is impossible to draw a line which separates these two types of patterns. So even this simple problem is also not solved using the perceptron. Also, most of the real world data is not linearly separable. You cannot, suppose you have data like this. Suppose blue bullet represents the output as 1, red bullets represents data points for which output is 0. You cannot linearly separate these two types of patterns, right? Here also you cannot separate it linearly. So we need a computational units or computational model which can deal with such data, right? So with a single perceptron, we cannot solve it, but using a network of perceptrons, we can solve such problem. So this is the network of perceptrons. For 2 inputs, I have taken 4 perceptrons at the middle level, and this is my output level. This is the perceptron at the output layer. So for this particular network of perceptrons, Palman, can I know how much time is left?
Ma'am, you can conclude in 5 minutes.
Okay, okay. So, okay, so what I say, using this particular network of perceptrons, you can so this particular network of perceptron has 3 layers, x1, x2. This is known as the input layer. Here, the 4 perceptrons we have kept. This is known as the hidden layer. Okay, middle layer containing the 4th perceptron is called the hidden layer, and the output layer has only 1 perceptron. So, using this model, we say that this particular network can be used to implement any Boolean function, whether it is linearly separable or not. Okay. See, for 2 inputs, we have kept 4 perceptrons in the hidden layer. If we have 3 inputs, you have to keep 2 raised to 3. That is 8 perceptrons at the middle layer. So it will increase. Definitely, it will increase the computational cost. But if you have no problem about the computational cost, then your problem can be solved, okay, using this particular architecture. So any Boolean function of n inputs can be represented exactly by a network of perceptrons containing 1 hidden layer with 2 raised to n perceptrons and 1 output layer containing 1 perceptron. Okay. So this is actually this theorem gives us the representation power of the multi-layer perceptron. This network which we have seen, this is known as the multi-layer perceptrons, right? Multi-layer perceptrons. And using this multi-layer perceptrons with a single hidden layer, we can represent any Boolean function. Okay. But what if? See, in the perceptron, we had Boolean, we had real inputs, but our output was Boolean, yes or no. Output was 0 or 1, right? But suppose my output is also real, then how to handle this problem? So we can have the network. We have to upgrade ourselves from perceptrons to the sigmoidal neurons. Okay. So I now stop with this discussion. Now, thank you very much. Now, any question?
Anybody is having any question from the audience? Any questions? So thank you, Trupti ma'am. That was a wonderful session, very informative all the basics covered, and you have explained us very nicely with examples too. Thank you so much, ma'am.
Thank you very much.
Thank you, ma'am. Thank you for sparing your precious time, ma'am. We would be looking forward to have more from you, and we will be inviting you for the further sessions too. Thank you so much, ma'am.
Thank you very much. Thank you.
Thank you. We can, yes, ma'am, we can end the session now. Thank you, Trupti, ma'am.
Thank you.
Have a nice day, madam.
Thank you. Same to you.
Have a nice day to all of you, all the participants. We can end the session now. Thank you so much, all of you.